the union of sets E alpha, let's say union, and we have a bunch of sets E alpha, and this alpha is a counter, okay, that runs on a set A. So we are going to write the union as a big capital U, E alpha, and then we say that alpha runs on the set A, belongs to the set A, okay? And this means, let's say that this is a set, so let's say that X belongs to the union if and only if there is at least one alpha such that X belongs to E alpha. Okay, or in other words, X belongs to E alpha for at least one alpha in A. Okay, so this is the definition. This means it could be for all of them, but the key point here is that at least one alpha. Okay. Usually, so we may have seen this already, right? If we take the set A, that is the set of natural numbers, right? So if it's a countable set, well, actually a finite set, then we will write the union, the union, let's say from alpha equal 1 all the way to n of the E alpha. Okay, and then if A is all the natural numbers, then we will write from alpha equal 1 to infinity of E alpha. This is what we call, the first one is a finite union, and the second one is a countable union. Okay. Now, the same way we have defined the union, we can define the intersection. Okay, so the intersection of the E alpha is going to be defined as follows. So X is in the intersection of the E alpha with alpha in A if and only if X belongs to E alpha for every alpha in A. Okay, so here the key point that we need to realize is at least one in the case of the union and for all in the case of the intersection. Okay. Again, well, I didn't say it before, but I say it now. This capital U, it's very similar to the notation for the sum, the sigma notation. Okay, so in this case, this would mean E1 union, E2 union, and so on all the way up to En. Okay. In the case of the intersection, we can write the union from 1 to n. Sorry, not the union, the intersection of the E alpha. Okay, this would be E1 intersection E2 and so on, intersection En. And we can also write a countable intersection going all the way to infinity. That means that we are taking all the possible positive integers. Okay. Some examples. So let's say we have three sets, the set of numbers 1, 2, and 3. Then the set of numbers 2, 3, and 4. And then the set of numbers, well, that's 4. Okay. Well, let's make it 4 and 5. Now, written like this, so I could write the union of E1 and E2, right? Would be every element that is in at least one. So 1 would be there because it's in E1, 2 and 3 also. 2 and 3 are in E1 and E2, but that doesn't matter. And then 4 that belongs to E2. Okay, but for example, the intersection in this case would be the ones that are in both of them. So it would be 2 and 3. Okay. Yes, that's one possibility. Then we could also decide, okay, let me check the intersection of all 3 sets. Well, actually, no, let's do 2 and 3. E2 intersection with E3. In this case, intersection is 4, right? And I could decide, okay, well, what is intersection with E1? In this case, they have no common elements, so the intersection is empty, right? So this means the 2 sets are disjoint. This is the empty set. So then E1, E2, E3, we say they are disjoint. Okay, or we could have written the intersection of E1, E2, and E3. In this case, it's also disjoint because all 3 of them have no common elements. Okay, they have common elements, E1 with E2, and then E2 with E3, but that's it. When you put all 3 together, there are no common elements. And let's do one more example. Let's say we have the set A of any number that is between 0 and 1. 0 is included, 1 is excluded. So this would be the real numbers such that 0 less than x less or equal than 1. So this is the set of counters. Okay. And then whenever I have x, okay, in this A, then I'm going to define EX as the set of real numbers y such that 0 less than y less than x. Okay, so this would be the interval 0x. Okay. So with these definitions, we could look at the union, right? Or in the intersection. Let's look at the union, sorry, the union of all of them when x runs through the whole A of the EX. What is this union going to be? So then let's do a picture to understand what's going on. So this is 0, this is 1. And then we have our sets that are like this. You see, as we move x, closer to 1, they get longer and longer and longer, right? And we will always get closer and closer to 1. Okay, so when we take the whole union, the whole union is going to be E1. Why? E1 means the interval 0, 1, open interval, okay? Why? Well, just pick any number, whatever you want here. It's just a matter of growing x until there is some interval here that passes that passes that value, okay? And any number that you pick that is not exactly equal to 1, that is less than 1, it's just a matter of time that some of these intervals ex runs through it. Okay, so it's always going to be included. Now, a little more subtle is the intersection. Okay, so what is the intersection of the ex? So this is a similar idea, right? But now it goes the other way around. So we have our intervals and they are going to be decreasing towards 0. Okay, and here the point is wherever you choose your x, or yeah, let's call it y in this case. Okay, you just need to wait, and eventually you will be on the left of that set. Okay, so there will be some ex that don't contain the element y, and this is for all y, x less than y. Okay, so that means that that any element you pick is not going to be in every single set ex. So then this intersection must be empty.